Hi everyone, my name is Timo Walter and I'm a committer in the Apache Flink software project. In these videos, I want to share knowledge about Apache Flink, stream processing, and general software engineering topics. In this video, I want to answer the question, what is Apache Flink? Apache Flink is an open source software project and is part of the Apache Software Foundation. And it is actually not so easy to answer the question, what is Flink? This here I have copied from the official website of Apache Flink. And there it tries to summarize Flink just in a couple of sentences. So what is Flink? In a nutshell, it's stateful computations over data streams. So it's a stream processor that has specialized on these stateful computations over data streams. But Flink is more than that. Flink is actually an entire framework, a kind of a platform, and it allows you to do distributed processing for stateful computations over both unbounded and bounded data streams. Flink has been designed to run in all common clusters and environments, including also locally on your PC, and perform computations at in-memory speed and at any scale. You can learn more on the website, and there is also a lot of documentation for Flink, but I also want to use this video here to quickly summarize what is so special about Flink and what is Flink used for. So maybe you have seen this slide in one of my other videos already. Flink is actually more than just a tool. I would usually consider Flink more of a toolbox. So Flink can serve a lot of different kinds of use cases, from analytical use cases to do like real-time analytics, real-time insights, data integration, piping data from A to B, doing ETL on the streaming data, and create event-driven applications. And also the input and output sources and systems are very diverse. So from messaging systems over databases, Flink is able to consume and produce data into different systems. And also, if you look at the left side, from transaction logs and IoT events, Flink is very flexible when it comes to what kind of data it can process. This slide here shows some usages that were posted in the official Apache Flink Slack channel. I haven't verified all the sources, so take this with a grain of salt. But in general, you can see the diversity also in the Flink community. So Flink is used for internal data cloud infrastructure. It is used for streaming analytics, for getting insights and quality of service telemetry. People have built security products that do real-time security analysis, a feature platform, feature generation system, and various kinds of real-time data processing services for smart buildings, for the Web3 even, for log management. So you can see that like also the users behind Flink, like they vary from traditional Fortune 500 companies over startups, from e-commerce to heavy IT tech companies, from gaming companies, over various other kinds of video platforms and so on. So Flink is used in the background at many data centers, and is very flexible also when it comes to use cases. And then often the question arises, okay, but what makes Flink so unique? So what is the difference between Flink and some other streaming system or some other stream processor? Like, how can I compare those stream processors with each other? And this is actually not so easy. What I will try now is to summarize it in one slide, animated slide here. First of all, how can you define a pipeline in Flink? actually is quite simple. You can imagine it as if you would draw some circles on a whiteboard. If you start designing a data pipeline, you would draw some circles for a source, for maybe a filter step, a normalization step. Maybe you want to join two sources together and then produce some data into a sink, right? Like this is how you would usually start. And conceptually, this is also what you define as a Flink pipeline. So the dots are operators and the dots are connected with arrows. And the arrows represent streams. Could be similar like this. The important piece here is you never have to think about parallelism, threading, network stacks or network buffers or serialization. Like most of the stuff that makes like distributed stream processing hard is actually abstracted away from you. So you define your source or your join task once, and Flink takes care of replicating and parallelizing the execution. So as you can see here, you define the join once, and then Flink will, for example, run it into subtasks. So like two parallel threads will actually execute the whole pipeline for a join. And yeah, same for maybe for a source, right? Like if you have a Kafka source with multiple partitions, I mean, in this case, we have only one partition, but the other source maybe has two shards. So yeah, like this one can be parallelized in parallel, and this one is just executed, processed with a parallelism of one. And maybe you have seen the video about what makes or what is a stateful stream processor, or what is a stream processor, and what are the building blocks for a good stream processor. And in this video, I talk about state, and state is also one of the most important factors that make Flink unique. So what is state? State, you can imagine state as a database, but instead of having a database somewhere outside of the system, which would increase the latency, the database is actually very close to the operator, close to what has to be done, to what has to be processed. So for example, in case of a join, maybe you need to wait for the other side. So maybe you have just received one event from one side, but the other side is still missing. So what you do is you put the event into state and you wait for the second event to arrive. So this is a typical state example. But state can also be at other locations that you might not see or that are not so obvious. For example, take a look at the source. The source is also stateful. For example, if it is a Kafka source, we would store Flink would store the offset, the Kafka offset, in the state. So Flink keeps track of where it has left off in the consumption of data, and instead it stores where it has to continue in case of a failure, for example. The important piece here is that the state is local to the operator. So when we scale out or scale in, the state can scale in and scale out together with the operator. And each lookup into the state is very efficient, almost at in-memory speed. So that makes the state lookups very efficient and improves the latency, because we don't have to go to an external database for lookups. And the way how all of that works, this is what makes Flink unique, because it does a very good job at maintaining state, managing state, and also persisting state. And this we can see in the next animation. So first of all, this is how Flink would operate during runtime, right? So we have events that traveling through the topology. This one is a shuffling step where we for example group by key, so that common keys meet at a common subtask. And yeah, as you can see, the common keys are then merged into this green symbol here, and then they are sent downstream. And of course, we have a filter here, so sometimes also some events are filtered out by the filter operator. And now comes the important thing that is required when state is involved. Yeah, how can we actually make a snapshot of our entire topology? And Flink is able to basically scan the whole streaming topology and store all the state involved in all the operators into a durable long-term storage. Could be, for example, an S3 bucket. And yeah, like once this is stored there, this durable snapshot can be used for fault tolerance in case some of the operators goes down, or it can be used for versioning your application to try out different versions of your application. And like this, the algorithm, the way how all of that is implemented, this is what Flink makes unique, because it's very difficult actually to create a stream processor that is able to perform a snapshot of a stateful application with exactly one guarantees. So you don't want to create any kind of duplicates in the end. So it is possible to have an end-to-end data integration pipeline that can also satisfy exactly one's guarantees. So yeah, that was a very, very quick introduction to Flink. I'm pretty sure there are also lots of better tutorials out there, so also search in the internet for more content. What I also want to quickly discuss are Flink's APIs. So how can I actually instruct Flink to do things for me? So this is the API stack in Flink. We have basically 3 APIs that are currently in the code base. I don't want to go into the details of stateful functions because it's currently on the deprecation path, so it won't be a big thing in the future. But I want to focus on the 2 core APIs in Flink, which is the DataStream API and the Table API. All APIs built on top of Flink's data flow runtime, Flink's data flow engine. This is a real streaming engine, a real data flow engine that is not based on any kind of, it's not based on Kafka, it's not based on mini batching or Hadoop or whatever. No, this is a purely Flink custom runtime targeted to what we want to achieve with Flink. And on top of this runtime, we have a low-level stream operator API, and both the DataStream API and the Table API access this low-level API. And as you can see, the DataStream API goes directly against this low-level one, so you can achieve a lot here. But there is also the Table and SQL API, and this Table and SQL API has a planner and optimizer between the API and the low-level API. So that means the planner can do things smarter. It can optimize and can improve the pipeline in a way that a regular DataStream API user would need very deep knowledge about before it can be as efficient as the SQL engine. So these are the big differences. So either you go through a static topology, or you just use a declarative topology that has an optimizer and planner in between. So let's take a look at the APIs and some examples. So this is a typical DataStream API tiny example. You start with a stream execution environment. You can set the runtime mode because you can run both in streaming or in batch mode. Batch mode would be a special case of the streaming mode for efficient execution on bounded streams. Like we can create a dummy stream here. We can call from elements 1 to 3. This gives us a dummy stream of integers. And yeah, we can execute this stream in the Flink cluster, and then we can collect the results back into our local client, and we can also print our results locally in the console. And this is the output that this tiny example would give us. So the important properties to repeat it about DataStream API are: DataStream API exposes the building blocks that are there for stream processing. So you can define arbitrary topologies yourself. Those topologies remain static, and yeah, you have built-in functions such as map, filter, process, and connect that help you in defining the topologies. The business logic is written in user-defined functions, so in code. And you can use arbitrary user-defined record types that flow between the operators. So the regular Java objects, for example. Interestingly, when we talk about change logs, conceptually the DataStream API is an append-only or insert-only log. So the DataStream API doesn't know about any kind of updates or something like that. It's append-only, insert-only. So now let's take a look at the Table and SQL API. Some people just call it Table API. Some people call it SQL API. Actually, the Table API is a different way of viewing streams. So everything is centered around table objects. So you view the stream as a table, and this makes it actually quite convenient to work with streams. So less concepts that you need to learn, and you can just use the Table API as you would use a database, a regular database. So here we start with table environment, and then you have the chance either to define the pipeline programmatically, or you define it as SQL. The result is the same. You can use from values, row 1 to 3, or you really use SQL and embed the SQL string in the method call. And again, we are calling execute and print, and we are executing the pipeline, retrieving the results locally, and print them to the console. So to summarize that, this API tries to abstract the building blocks for stream processing. So you don't directly see state or time or anything that makes up a stream processor. The operator topology can be fully defined by the planner because you just declare what needs to be done and the planner decides how it will be done. The planner also decides what kind of record types will flow between the operators. So there are some kind of internal records that flow between the operators, and these internal operators use all the different kinds of optimization. For example, they work on binary data, they do lazy serialization and lazy deserialization, all these tricks that you can play in an engine if you are in full control of the whole topology. And only if you collect or print results locally or in a function, you will actually see the row type. So the row type is made for users, is exposed in the Table API because it's just easier to work with a row type instead of these complex binary internal record types. And important to note here is, if we execute this example, the output will look slightly different. The output is not only 1 to 3, but it will also contain a change flag at the first as a prefix of the output for debugging purposes. And the change flag in this case tells you that all of those change entries or all of these records are insert only. But conceptually, the whole Table API and the whole SQL engine, they are working on change logs under the hood. So for example, when you do counting or joining, if the result is updating, you will see that in the output because you're producing a change log. But again, it comes with a lot of internal operators that are very convenient and very useful compared to bare metal DataStream API. So yeah, both APIs come with their pros and with their cons. You can also mix and match them if you like. And yeah, we will also go into more details in further videos. Here is just an example how you can mix and match. So in this case, there is a from DataStream method or a to DataStream method, so you can really go back and forth between the APIs, do some pre-processing in SQL, and then do the sophisticated logic in DataStream API, or vice versa. So that is up to you. It's possible, and like switching between the APIs is actually low overhead, so it's not that expensive to go to, for example, from SQL to DataStream and then back to SQL again, whatever is convenient for you. Yeah, I hope this was a helpful introduction, and yeah, like stay tuned for more videos, and thank you for watching.